Deep beneath your feet, hidden in the heart of our planet, lies a secret older than the mountains, older than the oceans, older than life itself. It's a message from the stars, written in the language of atoms, forged in the unimaginable fury of a dying sun. Picture this: billions of years ago, a massive star reached the end of its life and erupted in a cataclysmic explosion, scattering its guts across the cosmos. Those stardust remnants didn't just vanish into the void, they became the building blocks of planets, including Earth, and today, scientists are uncovering traces of that ancient supernova right here, locked inside the very core of our world. This isn't science fiction, it's a cosmic detective story written in the elements beneath us. Every time you pick up a rock or feel the ground beneath your shoes, you're touching the aftermath of an event so powerful it shaped the destiny of our solar system. How did these stellar fingerprints end up buried in Earth's core? What can they tell us about the violent beginnings of our home in the universe? The answers lie in the whispers of radioactive isotopes, the faint echoes of long-dead stars still resonating in the molten iron beneath the crust. We're about to embark on a journey that stretches across time and space, from the fiery death throes of ancient suns to the cutting-edge labs where scientists decode these celestial clues. You'll discover how supernova didn't just create the ingredients for planets, they left behind a breadcrumb trail of radioactive elements that act like cosmic clocks, helping us piece together Earth's origin story. This is more than just astronomy or geology, it's a tale of interconnectedness, proving that we're all made of stardust in the most literal way possible. So settle in, because by the end of this video, you'll never look at the ground beneath your feet the same way again. To understand how these heavy elements ended up in Earth's core, we need to step back to the moment of their creation. When a massive star, many times heavier than our Sun, exhausts its nuclear fuel, it doesn't fade away quietly. Instead, it collapses under its own gravity in a fraction of a second, then rebounds in a shockwave so powerful it outshines entire galaxies. This explosion, a supernova, is nature's ultimate alchemy lab. The temperatures and pressures are so extreme that atoms are ripped apart and reassembled into entirely new elements: iron, nickel, even gold and uranium. These heavy metals, forged in the heart of the dying star, are hurled into space at incredible speeds, seeding the cosmos with the raw materials for future planets. What's truly mind-blowing is that without these stellar explosions, Earth as we know it wouldn't exist. The iron in your blood, the gold in your jewelry, the uranium that powers nuclear reactors, all of it was once stardust scattered by supernova billions of years ago. But how did these elements find their way into our planet's core? When the young Earth was still a molten ball, heavier metals like iron and nickel sank toward the center, pulled by gravity. Lighter elements floated upward, forming the crust and mantle. This process, called planetary differentiation, acted like a cosmic sorting machine, concentrating supernova remnants deep underground. Today, scientists can still detect traces of these ancient stellar ingredients. Certain radioactive isotopes like iron-60 serve as cosmic timestamps. They don't occur naturally on Earth, their only origin is supernova. By measuring their presence in rocks and meteorites, researchers can pinpoint when and how nearby star explosions enriched our solar system. It's like finding a fingerprint at a crime scene, except the scene is 4.5 billion years old, and the suspect is a long-dead star. These clues tell us that our solar system formed in the aftermath of multiple supernova, their debris swirling together in the cloud that birthed the sun and planets. The next time you hold a piece of metal, remember, it's more than just an object. It's a relic of stellar violence, a fragment of a star that died so that worlds like ours could be born. And buried beneath your feet, the Earth's core still hums with the echoes of that explosion, a testament to the universe's endless cycle of destruction and creation. Meteorites aren't just space rocks, they're ancient messengers, carrying secrets from a time before Earth even existed. These cosmic fragments, some older than our planet, act like frozen snapshots of the early solar system, preserving chemical fingerprints of the violent stellar explosions that shaped it. Imagine holding a piece of a meteorite in your hand. You're not just holding a rock, you're holding a piece of history, a relic from an era when our corner of the universe was a chaotic construction zone, littered with the debris of dying stars. One of the most telling clues locked inside these meteorites is an isotope called iron-60. This rare form of iron doesn't form naturally on Earth. Its only birthplace is the heart of a supernova. When scientists find traces of it in meteorites, it's like discovering a timestamp from a stellar explosion that happened billions of years ago. The presence of iron-60 tells us that a massive star died nearby, showering our infant solar system with its remains. And because these isotopes decay at a predictable rate, researchers can even calculate when that explosion happened, piecing together a timeline of cosmic events that led to our planet's formation. But meteorites don't just hold one kind of stellar fingerprint. They're like cosmic archives, packed with elements forged in different types of supernovae, some from the violent deaths of massive stars, others from the collisions of ultra-dense stellar corpses. By studying the mix of isotopes inside them, scientists can reconstruct the recipe of stardust that went into making Earth. It's as if we're sifting through the ashes of an ancient cosmic fireplace, figuring out what kind of wood, or in this case, what kind of stars, burned to create the world we know today. What's even more astonishing is how far these clues have traveled. Some meteorites contain microscopic grains that predate our solar system, entirely tiny pieces of stardust that drifted through space for millions of years before getting trapped in the swirling cloud that became the sun and planets. These grains are like interstellar hitchhikers, carrying chemical signatures of stars that died long before ours was born. By analyzing them, we're not just learning about Earth's history, we're glimpsing the lives and deaths of stars that lit up the galaxy before our solar system even existed. This field of research, sometimes called stellar archaeology, turns meteorites into cosmic detective stories. Every layer, every isotope, every microscopic grain is a clue waiting to be decoded. And as technology advances, these space rocks keep revealing deeper layers of the past, showing us how the violent deaths of distant stars laid the foundation for everything we know, from the ground beneath our feet to the iron in our blood. Think of Earth's core as a time capsule, one buried not just underground but in the depths of cosmic history. The swirling molten metal at the center of our planet isn't just a geological curiosity. It's a vault preserving elements from some of the most violent events in the universe. Heavy metals like iron, nickel, and even platinum didn't originate here. They're the remnants of stars that lived fast, died young, and left behind a legacy woven into the very foundation of our world. What makes planetary cores so fascinating is their role as cosmic archivists. When Earth was still a molten mass taking shape, gravity acted like a cosmic centrifuge, pulling denser materials inward. This process didn't just separate rock from metal, it concentrated rare isotopes from supernova into the core's depths. Some of these elements, like tungsten-182, are the decayed remnants of even rarer isotopes like hafnium-182, which only forms in the extreme conditions of a collapsing star. Their ratios act like a chemical barcode, revealing how much stellar debris was mixed into the primordial soup of our solar system. Scientists have found similar fingerprints in the cores of other rocky worlds. Mars, for example, has a different ratio of these isotopes compared to Earth, hinting that it formed from a slightly different batch of stardust, perhaps enriched by a later supernova, or located farther from the stellar explosions that seasoned our planet's building blocks. Even moon rocks tell a story. Their composition suggests Earth's core locked away certain metals so thoroughly that when a giant impact blasted material into orbit to form the moon, those elements were already out of reach, buried too deep to be scattered. This isn't just about Earth. Across the solar system, planetary cores are like pages in a galactic history book. Mercury's oversized core, for instance, might hold clues to an ancient collision that stripped away its outer layers, leaving behind a metal-rich world. Meanwhile, asteroids like Psyche, a metallic body thought to be the exposed core of a failed planet, could offer a pristine sample of the raw materials that sank to the centers of worlds billions of years ago. The deeper we dig into these cosmic archives, the clearer the picture becomes. Our solar system didn't form in isolation. It was built from the ashes of countless stars, each explosion contributing its own unique mix of elements. By decoding the chemistry locked in planetary cores, we're not just learning about Earth's past, we're piecing together the life cycles of the stars that made our existence possible. Every earthquake, every volcanic eruption, even the slow churn of Earth's magnetic field, they're all echoes of a story that began in the hearts of dying suns. Those shockwaves rippling outward from dying stars did far more than sprinkle heavy elements across space. They were the cosmic spark that ignited the birth of our solar system. When a supernova explodes, it doesn't just eject material. It sends a titanic pressure wave racing through nearby gas clouds at millions of kilometers per hour. Picture a snowplow barreling down a quiet street, gathering loose powder into dense piles. Now imagine that plow is a wall of energy light years wide, and the snow is a vast, drifting cloud of hydrogen and stardust. That's the kind of force we're talking about, enough to compress entire nebulae into knots so dense, gravity could finally take over and begin sculpting new solar systems. This process, called triggered star formation, turns supernova into the ultimate cosmic architects. Before a shockwave arrives, gas clouds float in fragile equilibrium, too spread out to collapse on their own. But when that supersonic blast slams into them, it creates regions of extreme pressure, squeezing atoms together until they cross a critical threshold. Suddenly, pockets of gas become dense enough for gravity to pull them inward, sparking the chain reaction that forms stars and planets. Our own solar system likely owes its existence to one of these shockwaves, possibly from a supernova that erupted less than a light year away from our prenatal gas cloud. The evidence for this lies in the strange distribution of isotopes found in meteorites. Some contain radioactive aluminum-26, an element that forms only in supernova and decays rapidly, meaning it couldn't have traveled far before getting trapped in the infant solar system. Its presence suggests the explosion that seeded our neighborhood happened practically next door, flooding the area with fresh stardust just as the sun and planets were beginning to coalesce. It's as if the universe delivered a shipment of heavy elements just in time for construction, mixing them directly into the raw materials of Earth and its siblings. But shockwaves didn't just deliver ingredients, they shaped the entire construction site. Computer simulations show these pressure waves could have triggered turbulence in the gas cloud, creating whirlpools and eddies that helped material clump together faster. Without that chaos, the cloud might have remained too smooth and stable, delaying star formation for millions of years or preventing it altogether. In essence, supernova didn't just provide the bricks for building planets, they handed us the blueprints and gave the project a firm, universe-shaking nudge to get started. What's truly humbling is how precarious this chain of events was. If that shockwave had arrived a million years earlier, the gas cloud might not have been dense enough to respond. A million years later, the cloud could have already drifted apart. The timing had to be exquisitely precise, a celestial domino effect where one stellar death set the stage for new life. Every planet, every moon, every asteroid in our solar system exists because a star died at just the right place and time, its final act echoing across space to carve out a home for worlds yet unborn. Iron 60 is the cosmic equivalent of a smoking gun, a radioactive fingerprint that proves stellar explosions didn't just happen near Earth, but directly influenced its birth. Unlike stable iron isotopes, Iron 60 doesn't stick around for long. With a half-life of just 2.6 million years, any trace of it found on our planet today couldn't have formed here naturally. It had to arrive recently in cosmic terms, carried here by the debris of a dying star. Imagine finding a stopwatch still ticking in an ancient tomb. Iron 60 is that kind of evidence, a ticking clock that tells us exactly when and how supernova remnants rained down on our fledgling world. Scientists have hunted for this elusive isotope in some of Earth's oldest time capsules, deep-sea sediments and prehistoric crustal rocks. These layers act like geological tape recorders, preserving snapshots of our planet's chemical past. When researchers sifted through them, they found spikes of Iron 60 concentrated in layers dating back millions of years, like breadcrumbs left behind by passing supernova. One particularly telling deposit, found in ocean crust over 2 million years old, contains Iron 60 mixed with other supernova byproducts, proof that Earth was dusted with fresh stardust long after its formation. But here's what makes this discovery so revolutionary. Iron 60 doesn't just confirm that supernova happened nearby, it reveals they were close enough to matter. For these isotopes to reach Earth in detectable amounts, the explosions must have occurred within 100 light years or so, practically next door on the galactic scale. Any farther and the debris would have scattered too thin across space. These weren't distant fireworks, they were neighborhood events close enough to bathe our solar system in radiation and possibly even trigger climate shifts. Some researchers speculate that one such explosion, around 2.6 million years ago, might have contributed to the Pleistocene epoch's cooling, linking stellar death to changes in Earth's biosphere. What's even more astonishing is how Iron 60 helps us map the solar system's journey through the galaxy. As our Sun orbits the Milky Way, it occasionally drifts through dense molecular clouds or the remnants of ancient supernova. By dating Iron 60 deposits in different geological layers, scientists can reconstruct when we pass through these cosmic hotspots, like reading mile markers on an interstellar highway. One study suggests Earth may have spent over 100,000 years plowing through a cloud of supernova debris, collecting Iron 60 like a car windshield gathering raindrops on a stormy night. This isotope does more than connect us to the stars, it rewrites the story of our origins. Before Iron 60's discovery, astronomers assumed supernova were rare events, happening too far away to touch our corner of space. Now we know our solar system was born in a stellar nursery enriched by multiple explosions, each contributing heavy elements to the mix. Iron 60 is the timestamp on that recipe, proving Earth didn't just form from anonymous stardust, but from the ashes of specific cataclysmic stellar deaths. Every atom of it buried in our planet's crust is a signature from a star that died so we could exist, a reminder that the universe's most destructive forces are also its most creative. Digging into Earth's crust is like flipping through the pages of a cosmic history book. one where each layer holds clues about the violent stellar events that shaped our world. While most of the heavy elements from supernova sank into the planet's core during its molten youth, traces of this stardust still linger in the outermost layers, trapped like fossils in ancient rock formations. These aren't just random specks of metal, they're precise chemical signatures that reveal exactly which types of stars contributed to Earth's construction and when their debris arrived. Take the case of samarium and neodymium isotopes found in some of Earth's oldest rocks. These rare Earth elements act like cosmic stopwatches because they decay at predictable rates, allowing scientists to work backward and determine when supernova material was first mixed into our planet's building blocks. Rocks from Greenland dating back over 3.8 billion years show elevated levels of these isotopes, proof that stellar explosions were already seasoning the solar system's raw materials while Earth was still taking shape. What's remarkable is how these elements didn't just arrive in one delivery. Different rock layers show distinct pulses of enrichment, suggesting multiple supernova contributed ingredients over time, like chefs adding spices to a simmering pot. Some of the most surprising evidence comes from places you'd least expect, like the thin layers of sediment at the bottom of the ocean. In 2016, scientists drilling into the Pacific seafloor discovered a band of iron-60 mixed with sediment over 2 million years old. This wasn't just any layer. It correlated perfectly with a known period when our solar system drifted through a local bubble of interstellar gas, a region likely carved out by ancient supernova. The fact that this stardust settled evenly across the globe suggests Earth was literally showered with supernova debris, like a ship sailing through ashy fallout from a distant volcanic eruption. But the crust holds even older secrets. In Western Australia, researchers analyzing billion-year-old sandstone found microscopic grains of silicon carbide, a mineral that only forms in the extreme conditions of dying stars. These tiny time capsules predate the solar system itself, meaning they drifted through interstellar space for millions of years before getting trapped in Earth's rocks. Their crystal structures contain isotopic anomalies that fingerprint specific types of stars, allowing astronomers to identify not just that supernova contributed material, but exactly what kind of stars exploded. Some grains match the expected debris from red giants, while others bear the signature of rare hypernova, stellar explosions so powerful they defy conventional physics. What makes these crustal deposits so valuable is how they fill gaps in the meteorite record. While space rocks preserve pristine samples of early solar system material, Earth's constantly recycling crust offers something different, a timeline showing how supernova products were distributed and altered over billions of years. By comparing isotopes in ancient crustal rocks with those in meteorites, scientists can track how stellar debris was mixed into the planet during different geological eras. It's like having two history books, one preserving the original ingredients, the other showing how they were cooked into the final dish. Perhaps most astonishing is how these discoveries rewrite our understanding of Earth's relationship with the cosmos. The crust isn't just a passive container for supernova leftovers. It actively concentrates them in certain areas. Volcanic hotspots like Hawaii bring up material from deep within the mantle that's unusually rich in stellar isotopes, suggesting some supernova debris got trapped in isolated reservoirs rather than mixing evenly. Meanwhile, certain ore deposits like the nickel-rich mines of Sudbury in Canada contain metal ratios that mirror those found in meteorites, hinting at localized downpours of stardust during Earth's early bombardment period. These crustal clues do more than satisfy scientific curiosity. They reshape how we see our planet's place in the galaxy. Every earthquake that exposes fresh bedrock, every volcanic eruption that brings up deep-seated minerals, even the slow erosion of mountain ranges, they're all processes that reveal new pages in Earth's stellar autobiography. The ground beneath us isn't just dirt and rock. It's an archive of cosmic events written in atoms forged by stars that died so that worlds like ours could live. The story written in Earth's core is just one chapter in a much larger cosmic saga, and to read the full narrative, we need to compare it with other worlds. Take Mars, our rusty neighbor. While both planets formed from the same swirling cloud of stardust, their cores tell wildly different stories. Earth's molten iron heart generates a protective magnetic field, but Mars's smaller, cooler core lost its dynamo billions of years ago. This isn't just a difference in size, it's a clue about how supernova material was unevenly distributed across the early solar system. Martian meteorites contain higher ratios of certain isotopes like tungsten-182, suggesting the red planet formed from a pocket of the primordial cloud that was less enriched by later supernova debris. It's as if Earth got an extra helping of stellar seasoning while Mars was left with a plainer recipe. Then there's the Moon, Earth's constant companion with a core that's surprisingly metal-poor. When a Mars-sized object collided with early Earth, the debris that coalesced into our Moon inherited mostly lighter materials from the outer layers, while heavier elements like platinum and iridium remained locked in Earth's deep interior. This explains why lunar rocks have far lower concentrations of these supernova-sourced metals. The Moon's core is like a stripped-down version of Earth's, missing the rich inventory of stellar elements that sank to our planet's center before the giant impact occurred. These planetary contrasts reveal a solar system far more diverse than we once imagined. Mercury's enormous core, making up nearly 85% of its diameter, hints at a violent past where collisions blasted away its outer layers, leaving behind a metal-rich world that's practically a naked planetary core. Meanwhile, asteroid belt oddities like Psyche, a 200-kilometer-wide metallic body, may be the exposed remnants of a failed planet's heart, offering a pristine sample of the raw materials that sank to the centers of larger worlds. Each of these celestial bodies preserves a unique snapshot of how supernova debris was sorted and separated during planetary construction. What's truly groundbreaking is how these differences help scientists reconstruct the solar system's birth environment. The varying isotope ratios between worlds act like cosmic measuring cups, showing how much stellar material was mixed into each planet's building blocks. Earth's abundance of certain metals suggests it formed in a region repeatedly enriched by nearby supernova, while Mars's composition points to a quieter corner of the nursery. Even tiny differences in metal ratios between the Earth and Moon have become precise tools for dating the giant impact that created our lunar companion. This comparative planetology is rewriting our understanding of cosmic chemistry. Just as no two snowflakes are identical, no two planets formed from exactly the same blend of stardust. The cores of these worlds are like fingerprints, each bearing the distinct marks of the stellar explosions that contributed to their creation. By deciphering these variations, we're not just learning about other worlds, we're uncovering the detailed recipe that made our own planet possible, one supernova remnant at a time. Here's a cosmic head-scratcher. If supernova littered space with iron, why is Earth's core missing so much of it? You'd think after all those stellar explosions, our planet would be swimming in the stuff. Yet when scientists calculate how much iron should be buried in Earth's core based on supernova models, the numbers don't add up. We're talking about a deficit of metal that could form an entire additional core the size of Mercury. So where did it all go? One compelling theory points to Earth's violent toddler years. Picture the early solar system as a demolition derby, protoplanets smashing together, fragments flying everywhere. During these catastrophic collisions, some researchers suggest massive impacts could have literally blasted chunks of Earth's iron-rich core into space. Imagine a titanic collision so powerful it vaporized part of our planet's metallic heart, scattering it across the solar system or even ejecting it entirely. This wouldn't just explain the missing iron, it could also solve another mystery: why moon rocks have such tiny amounts of certain metals. If Earth's core was still forming when the moon was created, some of that iron might have been lost before it could fully settle. But collisions aren't the only suspects. Some iron might be hiding in plain sight, trapped in Earth's mantle like treasure sunk in thick molasses. Under extreme pressures, iron can form compounds with oxygen or sulfur that behave differently than pure metal. These hybrid minerals might resist sinking to the core, lingering instead in the rocky layer above. Scientists have found strange pockets of dense material deep in the mantle using seismic waves, regions where seismic signals slow down dramatically. Could these be reservoirs of missing iron suspended in Earth's middle layers for billions of years? Experiments with diamond anvil cells, devices that crush tiny samples to mimic the mantle's crushing pressures, show iron can indeed get stuck in minerals like bridgmanite, the most abundant rock on Earth that no human has ever held. The plot thickens when we compare Earth to its siblings. Mercury's core makes up nearly 85% of its mass, way more than expected. Could some of Earth's lost iron have ended up there? It's unlikely through simple theft, but it hints that planetary cores aren't just random collections of metal. They're records of how each world formed in its own unique environment. Maybe Earth's iron wasn't stolen or misplaced, but simply distributed differently during its birth. Some models suggest early magnetic fields or swirling magma oceans could have altered how metals settled, leaving more iron mixed in the mantle than traditional theories predict. This isn't just academic curiosity. Solving the iron mystery could rewrite how we understand planetary formation. If significant iron avoided the core, it means Earth's internal chemistry is more complex than we thought, with consequences for everything from volcanic activity to magnetic field generation. That missing iron might even hold clues to why our planet developed plate tectonics, a process crucial for maintaining a habitable climate. Every percentage point of iron that didn't sink to the core could have altered Earth's thermal evolution, changing how heat escapes from its depths over billions of years. What's fascinating is how this puzzle connects to the broader cosmos. Exoplanet hunters have found worlds with densities that make no sense unless they, too, have missing or redistributed metals. By cracking Earth's case, we might unlock secrets about planets light years away, worlds where iron could be hiding in mantles, lost to space, or transformed into exotic states we've yet to discover. The universe has a way of balancing its books, even if we're still learning how to read them. That gold ring on your finger or platinum watch on your wrist isn't just jewelry. It's a piece of interstellar history forged in the most extreme conditions the universe can muster. While common elements like iron and nickel sank into Earth's core during its molten youth, precious metals like gold, platinum, and uranium arrived fashionably late to the party, delivered by cosmic events so violent they make ordinary supernova look tame. These glittering elements didn't come from the same stellar explosions that supplied our planet's iron heart. Instead, they're likely the fallout from rarer, more exotic catastrophes, like the collision of two neutron stars, an event so energetic it briefly outshines entire galaxies. Picture this: two ultra-dense stellar corpses, each packing more mass than our Sun into a city-sized sphere, locked in a death spiral. When they finally collide, the impact unleashes shockwaves that rip atoms apart, creating a maelstrom of neutrons so intense they force heavy elements to form in seconds. This process, called rapid neutron capture, or the R process, is nature's ultimate pressure cooker for crafting gold, platinum, and other precious metals. The explosion flings these newly minted elements into space at incredible speeds, where they eventually mix with gas clouds that form new generations of stars and planets. What's remarkable is how recently this stardust arrived. While Earth's core formed over 4 billion years ago, certain gold deposits in Earth's crust show isotopic signatures suggesting they were delivered later, possibly by a neutron star merger that happened within 1,000 light years of our solar system, just 100 million years before Earth finished forming. Unlike iron that sank to the core, these precious metals stayed near the surface because they chemically bond more easily with sulfur and oxygen, hitching rides on rising magma plumes to become concentrated in crustal veins we mine today. The evidence isn't just in Earth's rocks, it's written in meteorites too. Certain primitive space rocks contain gold to platinum ratios that match exactly what computer models predict from neutron star collisions. Even more telling, the abundance of these metals in our solar system is about what you'd expect from one or two nearby neutron star mergers during its formation. It's as if the universe scheduled a special delivery of luxury materials after Earth's core had already taken shape, sprinkling our crust with cosmic treasure. This changes how we view our planet's relationship with the cosmos. Gold isn't just rare on Earth, it's rare in the universe because the conditions needed to create it are so extreme. All the gold ever mined in human history could fit into 3 Olympic-sized swimming pools, and that scarcity reflects its extraordinary origins. When you hold a gold coin, you're holding material that may have traveled billions of years across space, forged in a flash of unimaginable violence before finally coming to rest in your hand. The next time you see a piece of jewelry, remember, its luster isn't just a reflection of light, but of cosmic history. That metal was once part of stars so dense a teaspoonful would weigh as much as Mount Everest, transformed through collisions that shook the fabric of space-time. These elements connect us not just to any stellar deaths, but to the universe's most spectacular fireworks, events that turned emptiness into treasure and left behind the rarest gifts buried in the ground beneath our feet. Neutron star collisions are the universe's ultimate alchemists, events so powerful they can forge gold in seconds. While supernovae get most of the attention for creating heavy elements, these ultra-dense stellar mergers operate on a whole different level. Imagine 2 city-sized objects, each containing more mass than our Sun, spinning around each other hundreds of times per second before colliding with the energy of 1 billion suns. The resulting fireball creates conditions so extreme that atoms are ripped apart and reassembled into elements far heavier than what typical supernova produce. This process, called rapid neutron capture or the R process, bombards atomic nuclei with so many neutrons that they grow into platinum, gold, uranium, the periodic table's most exotic members. What makes these events special isn't just their destructive power, but their precision as element factories. While a supernova scatters its products across light years, neutron star mergers focus their energy into narrow, ultra-hot jets packed with neutrons. Computer simulations show these jets act like cosmic assembly lines, with atomic nuclei getting pummeled by neutron waves so intense they skip dozens of steps on the periodic table in milliseconds. The gold in your jewelry might contain atoms that spent less than a second as unstable, neutron-rich isotopes before decaying into their final form, a blink compared to the millions of years some supernova-forged elements take to stabilize. The proof isn't just theoretical. In 2017, astronomers detected gravitational waves from a neutron star collision, along with a corresponding flash of light. Spectroscopic analysis of that light revealed telltale signatures of heavy elements being synthesized in real time, the first direct evidence that these events create cosmic gold mines. Even more compelling, the amount of heavy elements produced matched predictions almost perfectly, with an estimated 10 Earth masses worth of gold and platinum ejected in that single event. This changes how we view Earth's composition. Traditional models assumed supernova supplied most of our planet's heavy elements, but neutron star mergers could have contributed crucial extras. Certain platinum-rich deposits in Earth's crust show isotopic ratios that align better with our process production than supernova debris. There's also the timing. These mergers happen less frequently than supernova, but when they occur, they deliver concentrated payloads of precious metals. It's possible our solar system drifted through the fallout of one such event during its formative years, receiving a late but lavish delivery of materials that became concentrated in Earth's accessible layers rather than sinking to the core. The implications stretch far beyond our planet. Galaxies with higher rates of neutron star collisions show correspondingly higher abundances of our process elements in their stars. Some dwarf galaxies have stars containing 10 times more europium, and our process signature element, than similar stars in the Milky Way, suggesting they experienced particularly intense waves of neutron star mergers early in their history. This cosmic unevenness means planets in different parts of the galaxy could have radically different inventories of precious metals depending on their neighborhood's merger history. What's humbling is realizing how much of Earth's story depends on these rare cataclysmic events. The same forces that create black holes also sprinkled our world with the elements that made technology possible. Your smartphone contains about 50 milligrams of gold material that likely began its existence in the furious aftermath of two dead stars tearing each other apart billions of years ago. These collisions aren't just astronomical curiosities. They're the reason our planet contains the building blocks for everything from dental fillings to nuclear reactors. The universe writes its history in violence, and Earth's crust holds the receipts. Recreating the fury of a dying star in a laboratory might sound like science fiction, but it's exactly what nuclear physicists do to unravel the mysteries locked inside Earth's core. Using facilities like the National Ignition Facility in California or particle accelerators in Germany, scientists compress atoms to pressures exceeding 100 billion times Earth's atmosphere, conditions matching those in a supernova's heart. These experiments aren't just about brute force, they're precision reconstructions of the universe's most extreme chemistry sets, tracking how atomic nuclei behave when star-like temperatures and pressures tear them apart and rebuild them into heavier elements. One groundbreaking approach involves firing powerful lasers at tiny gold capsules filled with hydrogen isotopes. The instant the laser hits, temperatures soar past 100 million degrees hotter than the sun's core for a fraction of a second. In that blink of cosmic time, elements fuse and decay just as they would during a supernova, allowing researchers to measure the exact ratios of metals like iron, nickel, and platinum that such explosions produce. What's astonishing is how these miniature stellar explosions match the element signatures found in meteorites, confirming that supernova really did sprinkle our solar system with the seeds of planetary cores. Particle accelerators take a different approach, slamming atomic nuclei together at nearly light speed to simulate the chaotic particle soup of a collapsing star. By tweaking the energy and angle of collisions, physicists can recreate specific moments in a supernova's chain reaction, like when a shockwave rips through layers of stellar material, transforming silicon into iron or uranium in microseconds. Recent experiments at the GSI Helmholtz Center in Germany successfully synthesized rare isotopes like calcium-48, a key ingredient in planetary cores that only forms under extreme stellar conditions. But perhaps the most unexpected tool in this cosmic reconstruction is the humble supercomputer. Advanced simulations like those run at Oak Ridge National Laboratory stitch together data from lab experiments with astrophysical models, creating digital supernovae that unfold over weeks instead of seconds. These virtual explosions reveal nuances impossible to catch in physical experiments, like how turbulence in the collapsing star affects which elements get flung into space versus swallowed by the resulting black hole. One simulation showed iron isotopes spiraling outward in intricate whirlpool patterns, explaining why some meteorites contain pockets of iron-60 while others don't. What makes these experiments revolutionary isn't just their technical prowess, it's how they bridge the gap between astronomy and geology. By matching lab-created element ratios to those found in Earth's deepest rocks, scientists can pinpoint which types of supernova contributed most to our planet's core. Certain nickel-to-cobalt ratios, for instance, suggest Earth's building blocks were enriched by both massive core collapse supernova and rare type Ia explosions from white dwarf stars. This dual signature implies our solar system formed in a stellar nursery, littered with the debris of multiple star deaths, a cosmic melting pot where different stellar recipes blended together. The next frontier, recreating neutron star collisions, the universe's ultimate gold factories. New laser facilities coming online in Europe aim to simulate the incomprehensible densities of these mergers, where a sugar cube-sized chunk of material would weigh as much as Mount Everest. If successful, these experiments could finally explain why Earth's crust holds more gold than traditional supernova models predict. Every zap of a laser, every particle collision, every line of simulation code brings us closer to reading the stellar recipe written in the ground beneath our feet, one atomic nucleus at a time. Scattered across the Milky Way like cosmic fossils, ancient star clusters serve as time capsules from the universe's childhood. Among these, globular clusters stand out, dense collections of hundreds of thousands of stars bound together by gravity, many nearly as old as the galaxy itself. What makes them extraordinary isn't just their age, but their composition. These stellar relics contain stars forged from material enriched by the very first supernova, carrying chemical imprints of the universe's earliest element factories. Unlike younger stars that formed from well-mixed galactic material, these primordial clusters preserve the raw ingredients of a time when heavy elements were still rare treasures in the cosmos. Take Omega Centauri, one of the Milky Way's largest globular clusters, visible to the naked eye from southern latitudes. Spectroscopic analysis reveals its oldest stars have surprisingly low amounts of elements like iron, but curiously high levels of certain rare earth metals. This peculiar mix matches predictions for second-generation stars, born from gas clouds polluted by the explosions of the universe's first massive stars. Those pioneer supernovae, known as Population 3 stars, were giants hundreds of times more massive than our Sun, living fast and dying young in spectacular explosions that seeded space with its first heavy elements. The stars in Omega Centauri act like cosmic scribes, recording the output of those long-vanished titans in their atmospheric chemistry. But the real breakthrough came when astronomers noticed something unexpected. Not all ancient clusters share the same chemical fingerprints. Some, like Messier 92, show distinct groupings of stars with different element ratios, suggesting they formed from multiple waves of supernova debris. It's as if we're seeing snapshots of different stellar kitchens, each contributing its own unique blend of ingredients to the galactic pantry. This variation hints at a chaotic early universe where supernova didn't evenly enrich space, but created localized pockets of element-rich gas that gave birth to distinct stellar generations within the same cluster. The most fascinating clues come from so-called blue stragglers, or stars in these clusters that appear mysteriously young. These outliers turn out to be cosmic cannibals, formed when older stars collided and merged, mixing their ancient interiors with fresh surface material. By studying their composition, researchers can peer deeper into the chemical legacy of early supernova than standard stellar atmospheres allow. Some blue stragglers contain surprising amounts of elements like europium and gold metals that only form in the most extreme stellar explosions. Their presence in such old stars suggests neutron star mergers were already seasoning the universe with heavy elements barely a billion years after the Big Bang. What's emerging from these studies is a radical rewrite of galactic history. Instead of a smooth, gradual enrichment of elements across the Milky Way, we're seeing evidence of a lumpy, uneven process where certain regions got heavy metal hotspots from nearby supernova while others remained pristine. This explains why some ancient stars in these clusters have 50 times less iron than our Sun, while others, born just slightly later from better polluted gas, have nearly modern compositions. The clusters essentially froze these chemical differences in time, giving us a stratified record of how supernova products spread through the early galaxy. Modern telescopes are now taking this research even further. The James Webb Space Telescope's infrared eyes can analyze the chemical makeup of stars in distant globular clusters orbiting other galaxies, revealing whether this patchy enrichment was universal or unique to the Milky Way. Early results from galaxies like Andromeda show similar patterns, suggesting this stop-start element production might be a fundamental feature of how all galaxies grow up. Every ancient star cluster we study adds another piece to the puzzle, helping us understand not just where Earth's heavy elements came from, but how the universe learned to build planets in the first place. These stellar time capsules do more than satisfy our curiosity. They connect us directly to the universe's formative years. The same supernova that enriched those ancient clusters eventually contributed material to the gas cloud that formed our solar system. In a very real sense, the iron in Earth's core and the calcium in your bones were created under similar conditions to the elements we now study in stars billions of years older than our Sun. The universe remembers its history in the atoms it creates, and globular clusters are some of its most faithful archivists. The early solar system was no serene cosmic nursery. It was a demolition derby on a galactic scale, where newborn planets dodged celestial shrapnel and gravitational bullies reshaped orbits overnight. Picture a vast construction zone littered with the wreckage of failed worlds, crisscrossed by rogue planetoids, and periodically lit up by nearby supernova flashing like cosmic camera bulbs. This wasn't just background noise, it was the crucible that determined which worlds would inherit the richest deposits of stardust. Earth's final inventory of supernova leftovers, the very metals that sank into its core depended largely on where it happened to be orbiting during this chaotic era. Gravitational tugs from giant planets like Jupiter acted like cosmic pinball bumpers, flinging smaller bodies into new trajectories. Some were ejected entirely, becoming interstellar orphans. Others spiraled inward, delivering precious stellar metals to the inner planets in violent collisions. Computer simulations show these gravitational interactions created delivery windows, brief periods when debris from recent supernova could rain down on Earth more heavily. One such window may have opened around 4.5 billion years ago, when Jupiter's migration scattered nearby planetesimals, funneling metal-rich material toward the inner solar system like a celestial conveyor belt. The evidence lies in the irregular distribution of isotopes across different meteorite families. Some space rocks, like carbonaceous chondrites, carry higher concentrations of supernova-produced elements like aluminum-26, suggesting they formed closer to where stellar debris was concentrated. Others, like those from the asteroid Vesta, show much less enrichment, hinting they accreted in quieter regions farther from the chaos. Earth likely received its share through a mix of direct impacts and second-hand deliveries, with some metals arriving pre-packaged in smaller bodies that later collided with our planet. This wasn't a gentle process. The late heavy bombardment period, a cosmic hailstorm around 4 billion years ago, saw Earth pummeled by asteroids and comets at a rate hundreds of times higher than today. While these impacts scarred the young planet's surface, they also delivered a final wave of heavy elements, some of which sank through the molten mantle to join the core. The Moon's pockmarked face preserves a record of this violent epoch, with its oldest craters dating back to the same era when Earth's metal inventory was being finalized. What's fascinating is how neighboring worlds tell different stories. Mars, with its weaker gravity, may have lost much of its early atmosphere to these impacts, along with volatile elements that Earth retained. Mercury's oversized core suggests it either formed in a metal-rich pocket of the solar nebula or had its outer layers stripped away by collisions. Even asteroids like Psyche, thought to be an exposed planetary core, show unique metal ratios that reflect their individual histories of bombardment and fragmentation. This chaotic period did more than deliver materials. It shaped Earth's very architecture. The same impacts that brought metals may have also triggered the giant collision that formed our Moon. The heat from radioactive elements like aluminum-26 kept Earth's interior molten longer, allowing heavier metals to fully separate into a distinct core. And the gravitational shuffling of planets likely prevented Earth from growing even larger, freezing our metal inventory at just the right size to maintain a protective magnetic field without becoming a barren, super-dense world like Mercury. The violence of the early solar system wasn't random destruction. It was nature's way of sorting and distributing the legacy of dead stars. Every earthquake that ripples through Earth's crust, every shift of its magnetic field, even the slow churn of plate tectonics, are echoes of that formative era when our planet's fate and its core's composition was hammered out in cosmic collisions. The ground beneath your feet carries scars from battles fought billions of years ago, battles that determined how much stardust would remain locked in Earth's heart forever. Stretching across the vast emptiness between stars, invisible to the naked eye, float immense clouds of supernova dust, each grain a tiny tombstone marking the death of a star. Modern telescopes like the James Webb Space Telescope peer into these cosmic graveyards, not with sorrow, but with scientific fascination. These drifting clouds carry the elemental ashes of stellar explosions, and by studying their composition, astronomers can measure how much star-forged material survives the harshness of space to become building blocks for new worlds. One of the most revealing discoveries came when scientists turned Webb's infrared gaze toward the Crab Nebula, the shattered remains of a supernova observed on Earth in 1054. The nebula's swirling dust contains unexpected amounts of silicon and carbon, elements that typically get destroyed in stellar explosions. Their survival suggests supernova aren't just destructive events. They are also surprisingly efficient recycling plants, ejecting some material gently enough to preserve complex molecules. This changes how we view the journey of stardust. Instead of being vaporized and reformed, some atoms may have traveled billions of years intact, eventually landing in planets like Earth with their original chemical signatures still readable. But not all supernova dust gets so lucky. The interstellar medium, the sparse gas and dust between stars, acts like a cosmic blender, churning and eroding debris over millennia. Observations from the Atacama Large Millimeter Array in Chile show how shockwaves from subsequent supernova can shred older dust clouds, pulverizing them into smaller fragments or even vaporizing them back into atoms. This means only certain types of stellar explosions, those occurring in relatively quiet neighborhoods, may produce dust sturdy enough to endure until new planetary systems form. The dust we see today represents the hardiest survivors of a brutal galactic gauntlet. What's truly groundbreaking is how these observations let scientists calculate delivery rates. By measuring the ratio of iron to hydrogen in distant dust clouds, researchers can estimate how much supernova material typically gets incorporated into young solar systems. The numbers are staggering. A single supernova can enrich an entire molecular cloud with enough iron to forge millions of Earth-sized cores, yet the distribution isn't uniform. Some regions, like the Orion Arm where our solar system resides, show higher concentrations of these metals, evidence of past supernova hotspots that may have preferentially seeded certain areas with planet-forming ingredients. These interstellar dust clouds also solve a long-standing puzzle about our own solar system's composition. Meteorites contain isotopes like aluminum-26 that shouldn't exist unless our cosmic neighborhood was recently dusted by a supernova. Now, by comparing these meteorite ratios to those in modern supernova remnants, astronomers can confirm that yes, our solar system likely formed in a stellar nursery recently fertilized by at least one massive star's death throes. The same telescopes that study distant galaxies are, in effect, reading our own origin story written in the chemistry of deep space. Perhaps most mind-expanding is realizing we're watching this cycle continue in real time. In 2014, astronomers witnessed a supernova in the galaxy Messier 82 eject a massive dust plume, over 25% of the star's mass directly into space. 5 years later, follow-up observations showed that dust surviving and cooling, beginning its million-year journey to someday mix with a future generation of stars and planets. Every time you breathe, you inhale atoms that once undertook such a voyage, particles that rode light years on solar winds before becoming part of your body. The universe doesn't just have a history, it has a metabolism, and we're all part of its endless recycling of stardust. Buried within Earth's oldest rocks and meteorites lie nature's most precise timekeepers, radioactive isotopes ticking away like cosmic stopwatches since the birth of our solar system. Aluminum-26 and iron-60 don't just tell us that supernova influenced Earth's formation. They reveal exactly when those stellar explosions happened and how long it took for their debris to become part of our planet. Imagine finding a stopwatch frozen in time at the exact moment a star died. These isotopes work the same way, their decay rates acting as unchangeable timestamps in the geological record. Take aluminum-26, an isotope with a half-life of just 717,000 years. That's an eye blink in cosmic terms, meaning any aluminum-26 we find today couldn't have formed naturally on Earth. It had to arrive fresh from a nearby supernova just as the solar system was taking shape. When scientists analyze primitive meteorites, they find this isotope was once astonishingly abundant, 10 times more prevalent than in today's solar system. By measuring how much has decayed into magnesium-26, researchers can backtrack to pinpoint the moment that aluminum was forged, placing the supernova's explosion within a narrow window just a few 100,000 years before the sun's birth. It's like smelling smoke and realizing the fire must have been recent. The isotope's rapid decay leaves no doubt the stellar explosion happened right on our cosmic doorstep. Iron-60 tells an even more dramatic story. With a half-life of 2.6 million years, its presence in 4.5 billion-year-old meteorites is the equivalent of finding a still warm ember in ancient ashes. Unlike aluminum-26, which primarily heats planetary interiors as it decays, iron-60 acts as a direct tracer for supernova debris. Recent studies of deep sea crusts show Earth was still being dusted with fresh iron 62 million years ago, proof that our planet didn't just form from ancient stardust but continues drifting through the fallout of stellar explosions. The real power of these clocks comes when scientists cross-reference them. Aluminum-26's short half-life captures the supernova that likely triggered our solar system's collapse, while Iron-60's longer decay traces subsequent stellar explosions that enriched the young planets. Together, they form a layered timeline. Aluminum's decay reveals the initial spark of creation, while iron's persistence shows how later supernova may have delivered Earth's water or even influenced early climate. Some researchers speculate that a spike in Iron-60 around 2.6 million years ago coincided with a minor ice age, suggesting these cosmic timekeepers might do more than date rocks. They could link stellar events to shifts in our own biosphere. What's revolutionary is how these isotopes rewrite planetary formation stories. Traditional models assumed the solar system formed from well-mixed galactic material over millions of years. But Aluminum-26's rapid decay demands that the Sun and planets coalesced within less than 100,000 years of the supernova's arrival, a geological sprint rather than a marathon. This explains why some meteorites show extreme variations in isotope ratios. They formed at different times during this chaotic period, some capturing early supernova ejecta while others formed after further mixing. The clocks don't just tell time, they reveal the solar system's birth was more like a sudden storm than a slow drizzle, with waves of stellar debris arriving in distinct pulses rather than a steady rain. Today, these radioactive clocks are getting even more precise. Advanced mass spectrometers can now measure isotopic ratios down to parts per billion, allowing scientists to detect vanishingly small amounts of decay products. In Western Australia, zircon crystals dating back 4.4 billion years show traces of the original aluminum-26 heat that kept Earth's interior molten, while lunar rocks reveal how the Moon's formation reset some of these clocks entirely. Each measurement adds another tick to the cosmic metronome, helping us reconstruct not just when Earth formed, but the exact sequence of stellar events that made our existence possible. The next time you check your watch, remember, the universe has been keeping time far longer, using clocks forged in the hearts of dying stars. Every earthquake that shakes loose ancient rocks, every meteorite that falls to Earth, even the slow decay of atoms deep beneath your feet, they're all part of a chronology written not in hours and minutes, but in the half-lives of elements that witnessed the birth of worlds. The shockwave from a dying star might be the unsung hero of our solar system's origin story, a cosmic spark that transformed a drifting cloud of gas into the bustling planetary neighborhood we call home. Picture the pre-solar nebula 4.5 billion years ago, a vast, lazy swirl of hydrogen and dust, so diffuse that without some outside intervention, it might have lingered for millions more years before collapsing under its own gravity. Enter a nearby supernova detonating with the force of 1 billion suns. Its blast wave wouldn't just sprinkle heavy elements into the cloud, it would compress the gas like an invisible hand squeezing a balloon, triggering pockets of density where gravity could finally take over. This isn't just theoretical. Meteorites older than Earth itself contain radioactive isotopes like aluminum-26, which forms only in supernova and decays too quickly to have been lingering in the nebula. Its presence is like finding a still warm campfire in an ancient forest, proof that a stellar explosion happened shockingly close to our infant solar system, right as it was taking shape. Computer simulations show these shockwaves don't just nudge gas clouds, they create intricate webs of dense filaments like cosmic lightning bolts, where material collapses into protostars. The Orion Nebula, a modern stellar nursery, offers a glimpse of this process in action. Newborn stars often line up along shock fronts, as if birthed by some unseen pressure wave rippling through space. But supernova didn't just provide the push, they also delivered the recipe. The same blast that compressed the nebula would have flooded it with freshly forged elements, from iron and nickel to rare isotopes like calcium-48. These metals acted like seeds for planet formation, clumping together into the first solid particles that would eventually grow into asteroids, then protoplanets, and finally worlds like Earth. Without that stellar explosion's dual-role trigger and supplier, our solar system might have remained a sterile haze of hydrogen, never dense enough to ignite a sun or coalesce into planets. What's staggering is the precision of this cosmic timing. For the shockwave to hit just as the nebula reached a susceptible state, the supernova must have erupted within a few light years at most, a celestial bullseye. Too early, and the energy would have dissipated harmlessly. Too late, and the cloud might have drifted apart. It's as if the universe lined up a domino chain billions of years long, where one stellar death perfectly toppled into the birth of our solar system. Yet the influence didn't stop there. The supernova's debris likely continued raining down as the sun and planets formed, explaining why some meteorites show higher concentrations of certain isotopes than others. These variations are like geological timestamps, revealing waves of enrichment that came at different stages of construction. Even Earth's water, the foundation of life, might trace back to that explosion, as the heat and pressure of the shockwave could have unlocked water molecules trapped in interstellar dust grains. The takeaway is humbling. Every planet, every moon, even the sunlight warming your skin, exists because a star died at exactly the right place and time. Supernova aren't just destroyers, they're the universe's ultimate catalysts, turning chaos into structure with explosions so powerful they literally shape the architecture of solar systems. The next time you look up at the night sky, remember, you're not just seeing distant stars, you're witnessing the same process that made our existence possible, playing out again and again across the galaxy. Asteroids are more than just space rocks, they're time capsules holding pristine samples of the materials that built our solar system. While Earth's core remains locked away beneath miles of rock, metallic asteroids like Psyche offer a rare glimpse into the same metals that sank into our planet's heart billions of years ago. These cosmic relics never underwent the intense heating and differentiation that reshaped Earth, preserving their original composition like a snapshot of the early solar system's building blocks. NASA's upcoming mission to Psyche aims to study this metal-rich world up close, potentially uncovering secrets about how supernova debris was distributed during planetary formation. What makes these asteroids so valuable is their chemistry. Many contain alloys of iron and nickel nearly identical to what we believe exists in Earth's core, but with crucial differences in isotope ratios that tell us where they originally formed. Some meteorites, like the famous Campo del Cielo ions found in Argentina, contain traces of rare metals like iridium and osmium in concentrations far higher than Earth's crust, a fingerprint of their supernova origins. These exotic elements act like cosmic barcodes, revealing which regions of the primordial solar system were enriched by specific stellar explosions. By comparing these space rocks to Earth's composition, scientists can reconstruct which materials made it into our planet's core versus those that stayed near the surface. The real breakthrough could come from studying asteroids that formed farther out in the solar system. Carbonaceous chondrites, a type of meteorite rich in organic compounds, often contain microscopic diamonds with trapped noble gases, elements forged in supernova but preserved in these tiny, indestructible cages. These grains predate our solar system entirely, meaning they drifted through interstellar space before being incorporated into asteroids. Future sample return missions to asteroids like Bennu could bring back more of these ancient timekeepers, helping us map how supernova debris spread across different regions of the protoplanetary disk. But the Holy Grail would be sampling a metallic asteroid's interior. Most iron meteorites found on Earth are fragments from collisions that shattered their parent bodies long ago, leaving us with only exterior pieces. A mission that could drill into an intact metal asteroid might reveal layered deposits of elements, showing how supernova materials settled in varying concentrations as the solar nebula cooled. Some theories suggest the heaviest metals, like platinum and gold, may have condensed into metallic rain that pooled in certain asteroids like cosmic treasure chests holding the universe's rarest elements. The implications stretch beyond our solar system. By decoding how supernova remnants were distributed in our own neighborhood, we can better understand exoplanet compositions. A metallic core sampled from Psyche might explain why some distant worlds have unexpected densities, or why certain star systems show unusual metal ratios in their atmospheres. These asteroids aren't just relics, they're Rosetta Stones for interpreting the galactic recipe book of planet formation. Every scoop of asteroid dust, every laser scan of a metallic surface, brings us closer to answering the ultimate question: how much of Earth was built from stardust, and how much was pure cosmic chance? Astronomers have turned the galaxy into a crime scene, hunting for the remnants of ancient supernova whose fingerprints are all over Earth's core. This cosmic detective work starts by scanning the Milky Way for telltale signs of stellar explosions, expanding bubbles of gas, unusual concentrations of heavy elements, or the faint X-ray glow of radioactive decay. One prime suspect is the local bubble, a vast cavity in interstellar space stretching 300 light-years across, where multiple supernova likely exploded over the past 10 to 20 million years. Our solar system currently drifts through this region, suggesting we're still wading through the aftermath of those cataclysms. The iron-60 isotopes found in deep sea crusts and lunar soil match the expected debris from such nearby explosions, like finding ash from a long-extinguished fire still settling onto your windowsill. But identifying specific supernova that influenced Earth's formation requires sharper tools. Enter Gaia, the European Space Agency's star mapping mission, which has precisely measured the positions and motions of over 1 billion stars. By tracing stellar movements backward in time, astronomers can reconstruct where massive stars once lived and died. One groundbreaking study pinpointed a cluster of stars that 14 million years ago would have been just 100 light-years from Earth. These stars were massive enough to explode as supernova, potentially showering our planet with fresh radioactive isotopes during the Miocene epoch. The timing aligns eerily with minor extinction events in Earth's fossil record, hinting that stellar explosions might influence more than just geology. The search extends beyond visible remnants. Some supernova leave no glowing nebula behind, just a fast-moving neutron star hurtling through space like a bullet fired long ago. In 2019, researchers discovered one such runaway star, J1605, racing away from the Scorpius-Centaurus stellar association at speeds suggesting it was kicked by a supernova blast over 1 million years ago. Tracing its path backward leads to a region of space that would have placed the explosion dangerously close to Earth's prehistoric skies. While the visible evidence has dissipated, the star's trajectory acts like a cosmic breadcrumb, pointing to where the real action happened. The most tantalizing clues come from radioactive decay chains in Earth's crust. Certain isotopes like plutonium-244, with its 80 million year half-life, shouldn't exist naturally on our planet unless delivered by recent stellar explosions. Finding these in ocean sediments is like uncovering an atomic clock set by a dying star. When combined with Iron-60 data, they paint a picture of multiple supernovae peppering our solar system with heavy elements across different epochs, not just during Earth's formation, but throughout its history. This isn't just about the past. Our sun's orbit around the Milky Way means we'll inevitably encounter more supernova debris in the future. By mapping the distribution of young, massive stars along our galactic path, astronomers predict our next close encounter with a potential supernova progenitor could happen in the Orion Arm within the next few 100,000 years. While that might sound distant on cosmic timescales, it's a blink proof that Earth's relationship with dying stars is an ongoing saga, not just a chapter from our primordial past. The search for these stellar ghosts does more than satisfy curiosity. It rewrites our understanding of Earth as an isolated world. Every earthquake, every volcanic eruption that brings up deep-seated minerals, even the slow churn of tectonic plates, might ultimately trace back to shockwaves from stars that died before humans walked the Earth. The universe doesn't forget its explosions, and neither does the planet we call home. The same stellar furnaces that forged Earth's iron heart also cooked up the very ingredients of life itself. Carbon, oxygen, nitrogen, the building blocks of DNA, proteins, and every living cell were all born in the searing cores of stars and scattered across the cosmos by supernova. This isn't poetic metaphor, it's a chemical fact written in the atomic makeup of your body. The calcium in your bones, the iron in your blood, even the phosphorus that powers your cells, all were forged in stellar explosions that occurred long before our solar system existed. Without these cataclysmic events, life as we know it wouldn't just be rare, it would be impossible. Take carbon, the backbone of organic chemistry. Unlike heavier elements that sink into planetary cores, carbon's versatility allows it to form chains and rings, creating the molecular scaffolding for life. This element originates not from the violent deaths of massive stars, but from the quieter farewells of intermediate-sized suns, stars like our own, that puff away their outer layers in planetary nebulae. Yet even these gentler expulsions owe their existence to earlier supernova, which seeded the galaxy with the raw materials for subsequent generations of stars. It's a cosmic relay race where each stellar death passes the baton of complexity to the next generation. Oxygen tells an even more dramatic story. The second most abundant element in your body was created through a delicate balancing act inside massive stars, a process called helium burning that occurs only within a narrow temperature window. Too cold and the reactions stall, too hot and the oxygen gets destroyed to form heavier elements. Supernova play the critical role of preserving this carefully crafted oxygen by ejecting it into space before the collapsing star's core can consume it entirely. The result, an atmosphere rich in life-sustaining oxygen, oceans of water, and the very air we breathe, all gifts from stars that died billions of years ago. But supernova didn't just provide life's ingredients, they may have shaped its delivery system. Some theories suggest the radioactive aluminum-26 that supernova injected into the young solar system acted as an internal heat source for early Earth, keeping the planet geologically active longer. This extended warmth could have maintained the volcanic outgassing that created our atmosphere and the hydrothermal vents where life potentially first emerged. Meanwhile, the same shockwaves that triggered our solar system's formation might have carried complex organic molecules frozen onto dust grains like microscopic care packages from the stars. The evidence for this stellar connection isn't just theoretical. Meteorites like the Murchison specimen, which fell in Australia in 1969, contain amino acids, the same molecules that form proteins in living organisms. These space rocks prove that the basic components of life can form in interstellar space. likely aboard dust grains processed by shockwaves from nearby supernova. Even more telling, some of these meteoritic amino acids show left-handed molecular preferences, mirroring the bias seen in Earth's life forms, hinting at a possible cosmic origin for this biological quirk. What's truly humbling is realizing how precarious this chain of events was. The supernova that enriched our solar system had to explode close enough to deliver their elements, but not so close as to sterilize the region with lethal radiation. They had to occur at just the right time, after the universe had produced enough carbon and oxygen, but before all the primordial hydrogen fuel for stars was exhausted. Even Earth's position in the galaxy matters. Too close to the crowded center, and supernova would be too frequent for life to gain a foothold. Too far out in the sparse suburbs, and there wouldn't have been enough stellar explosions to provide the necessary heavy elements. This cosmic perspective transforms how we view our place in the universe. The same forces that created the metals in Earth's core also set the table for biology's emergence. Your every breath draws in atoms that were once part of stars, your every heartbeat powered by chemical reactions fueled by stellar nucleosynthesis. The boundary between astronomy and biology blurs. We're not just inhabitants of Earth, but temporary collections of stardust given consciousness, looking back at the stars that made us and wondering about our connection to them. The next frontier in this story lies in exoplanet research. As astronomers discover worlds orbiting other stars, they're finding correlations between a star's metal content, a proxy for its supernova enrichment, and the types of planets it hosts. Systems with higher concentrations of these life-critical elements seem more likely to form rocky worlds in habitable zones. We may soon find that Earth isn't unique, but part of a vast network of worlds sculpted by stellar deaths and nurtured by their elemental gifts, a cosmic garden where supernova plant the seeds of both planets and life. Earth's magnetic field isn't just an invisible force, it's a cosmic heirloom, a legacy of stellar explosions that shaped our planet's destiny. Picture a vast, swirling ocean of molten iron 4,000 miles beneath your feet, churning like a dynamo as Earth rotates. This relentless motion generates the magnetic shield that deflects deadly solar radiation, making life on land possible. But here's the twist: none of this would exist without the iron delivered by supernova billions of years ago. That protective field, which guides compasses and lights up auroras, owes its existence to stars that died before our solar system was born. The connection lies in Earth's core composition. When scientists analyzed seismic waves traveling through the planet, they discovered the outer core is primarily liquid iron and nickel, exactly the metals supernova produce in abundance. These elements didn't just randomly appear, they're the ashes of massive stars that exploded nearby, seeding the gas cloud that birthed our solar system. Without that stellar contribution, Earth might have ended up with a smaller, weaker core like Mars, unable to sustain a global magnetic field. The red planet's faded magnetic remnants serve as a stark warning. No rotating metal core means no protective shield, leaving the surface exposed to radiation that strips away atmospheres and boils off oceans. But supernova didn't just provide the ingredients, they influenced how those materials settled. Radioactive isotopes like aluminum-26, delivered by the same stellar explosions, kept Earth's interior molten longer during its formative years. This extended heat allowed heavier metals to fully separate from silicate rocks, sinking to form a distinct, liquid outer core capable of generating a strong magnetic dynamo. In contrast, smaller worlds like Mercury cooled too quickly, freezing their cores into static metal spheres. The Goldilocks balance of Earth's core, hot enough to stay liquid but massive enough to churn vigorously, wasn't luck. It was a direct result of the type and quantity of supernova debris mixed into our planet's building blocks. The field's importance goes far beyond compass needles. During solar storms, when the sun hurls charged particles at Earth at nearly the speed of light, our magnetic shield bends these particles toward the poles, where they ignite the dazzling northern and southern lights. Without this deflection, that same energy would fry satellites, disrupt power grids, and bombard living cells with radiation. Some researchers even argue that Earth's early magnetic field protected delicate organic molecules in shallow seas, giving life a chance to take hold. The same iron that supernova forged became the guardian of biology itself. Yet this shield isn't static. Geological records show Earth's magnetic poles have flipped hundreds of times, with the field weakening and strengthening over millennia. These fluctuations might trace back to uneven distribution of radioactive elements in the core elements like uranium and thorium that supernova peppered throughout the young solar system. As these heat-producing isotopes decay, they stir the molten iron like invisible spoons, altering convection patterns that power the dynamo. Even today, satellites detect mysterious hotspots where the magnetic field is unusually weak, possibly marking plumes of supernova-sourced elements rising from the core mantle boundary. The profound takeaway: our planet's ability to nurture life hinges on a chain of cosmic events stretching back to stellar deaths we'll never witness. The iron in Earth's core does more than anchor gravity. It spins an electromagnetic cocoon that took billions of years to weave. From the supernova that forged these metals to the precise timing of their delivery, every link in that chain had to hold for Earth to become the life-filled world we know. When you watch an aurora dance across the sky, you're seeing more than pretty lights. You're glimpsing the living echo of stars that died so we could live. The solar wind isn't just a stream of particles from the sun. It's a cosmic courier delivering faint whispers of ancient supernova straight to our doorstep. Every second, millions of charged particles race past Earth at speeds topping 1,000,000 miles per hour, and hidden among them are atoms with extraordinary origins. Some of these particles carry isotopic signatures that don't match anything produced by our sun. Instead, they bear the unmistakable fingerprints of long-dead stars, material forged in stellar explosions that predate our solar system by billions of years. NASA's Genesis mission, which collected solar wind particles in pristine collectors during its 2-year orbit, made a startling discovery when analyzing its samples back on Earth. Tiny traces of neon and oxygen isotopes matched the expected ratios from supernova nucleosynthesis rather than typical solar material. These atoms didn't originate in the sun's fusion processes. They were hitchhikers, clinging to the solar wind after being mixed into the protosolar nebula during the solar system's violent infancy. It's as if the sun's outer atmosphere contained stardust that never fully assimilated, preserving fragments of stellar history in its gusting winds. But how do these supernova relics persist for so long? The answer lies in the sun's own formation. When our star ignited, it didn't vaporize all the material swirling around it. Dust grains rich in heavy elements remained suspended in the protoplanetary disk, some eventually becoming part of asteroids or comets, while others were swept up into the sun's corona. There, in the million-degree outer atmosphere, these resilient grains slowly erode over billions of years, releasing their exotic atoms into the solar wind like time capsules cracking open. The solar wind becomes a museum of stellar archaeology, with each particle telling a story of where it came from and how it survived. Modern spacecraft like NASA's Parker Solar Probe are adding new chapters to this story. Flying closer to the sun than any previous mission, Parker has detected unexpected variations in solar wind composition, including brief spikes of iron and nickel isotopes that align with supernova production models. These metals shouldn't vaporize easily in the sun's atmosphere, suggesting they might arrive as microscopic dust particles from interstellar space, only to be broken apart and flung outward by the solar wind's relentless push. Some researchers speculate these could be the last remnants of a supernova shockwave that passed through our solar system within the last 100,000 years, its dust still filtering down through the heliosphere. What's truly remarkable is how these discoveries connect to the bigger picture of galactic chemistry. The same isotopes found in the solar wind also appear in Earth's upper atmosphere, where they've been detected by high-altitude balloons and research planes. This means supernova debris isn't just locked in rocks or buried in planetary cores, it's still raining down on us, blending with the air we breathe. The oxygen atoms in your next breath might include a few that last touched a star's fiery interior 5 billion years ago, survivors of an epic journey across space and time. The implications stretch beyond our solar system. Astronomers studying young stars often detect similar anomalous isotopes in their stellar winds, suggesting this process of supernova recycling is universal. Every newborn star likely inherits some fraction of its neighbor's explosive remains, carrying forward the legacy of stellar deaths in its own particle emissions. We're seeing the universe's grand cycle of destruction and renewal play out in real time, with the solar wind as our local example of how nothing in space ever truly disappears. It just changes form and continues the journey. Next time you feel the warmth of sunlight on your skin, remember, those rays carry more than just energy from the sun's core. Mixed into the light are atomic messages from stars that died before Earth existed, their final echoes still traveling through space, still reaching us, still reminding us that every particle in the cosmos has a story to tell. The mysteries hidden in Earth's core may not stay buried forever. Cutting-edge technology is giving scientists unprecedented tools to probe these depths like never before. Imagine sending seismic waves through the planet and receiving back not just vague echoes, but high-resolution snapshots of the core's composition, down to the atomic level. That's the promise of next-generation seismology, where networks of ultra-sensitive sensors and AI-powered analysis are transforming how we see inside our planet. Recent advancements in quantum gravity sensors, for example, can detect minute variations in Earth's gravitational field caused by dense pockets of iron and nickel, potentially revealing concentrations of supernova-sourced metals that settled unevenly billions of years ago. Space missions are set to revolutionize this field from another angle. NASA's upcoming Psyche mission to the metal-rich asteroid of the same name isn't just exploring a curious space rock, it's offering a window into Earth's inaccessible core. Psyche's composition likely mirrors the primordial material that sank into our planet's center during its formation. By studying its surface with gamma-ray spectrometers and neutron detectors, scientists can indirectly map the distribution of elements like platinum, iridium, and gold in Earth's core without drilling a single mile. Already, prototype instruments for these missions have uncovered surprises in meteorites, such as unexpected ratios of tungsten isotopes that hint at supernova debris arriving in distinct waves during the solar system's infancy. But the real game-changer lies in combining these approaches. Cross-referencing seismic data with findings from space missions allows researchers to build 3D models of Earth's core that account for both its current state and its cosmic origins. For instance, anomalies in seismic wave speeds like the mysterious ultra-low velocity zones detected near the core mantle boundary could be explained by localized deposits of supernova-produced heavy elements. Lab experiments replicating core conditions using diamond anvil cells and synchrotron X-rays now suggest some of these zones might contain exotic iron-oxygen alloys that only form under extreme pressures, offering clues about how stellar material behaved during Earth's violent early years. The future holds even bolder possibilities. Projects like the Deep Earth Carbon Observatory are developing sensors capable of detecting neutrinos, ghostly particles emitted by radioactive elements decaying in Earth's core. Since isotopes like potassium-40 and uranium-238 are byproducts of supernova, mapping their distribution could reveal which regions of the core are richest in stellar debris. Meanwhile, proposals for lunar seismology aim to place detectors on the Moon to analyze moonquakes caused by Earth's gravitational pull, providing an off-world vantage point to study our planet's deep interior. What excites researchers most is how these tools might solve long-standing puzzles. Why does Earth's core contain less iron than predicted by supernova models? Could some be locked in mantle reservoirs as yet undiscovered? Could variations in the magnetic field's strength trace back to patches of core material enriched by different stellar explosions? Each question leads back to the cataclysmic stellar deaths that shaped our world. Within the next decade, as computational models grow more sophisticated and interplanetary missions return fresh data, we may finally read the full story written in Earth's heart, a narrative of supernova, solar system chaos, and the improbable alchemy that turned Stardust into a living planet. Our solar system's story isn't unique. Supernova have left their fingerprints on planetary systems across the galaxy, and the growing catalog of exoplanets is revealing just how diverse those fingerprints can be. Take the Kepler system, where astronomers discovered a planet twice Earth's size orbiting a star rich in heavy elements. This world, known as Kepler 10c, shouldn't exist according to traditional models. Its density suggests a rocky composition, yet it's far more massive than expected for a planet of its type. The likely explanation: its parent star formed in a region blasted by multiple supernova, packing the protoplanetary disk with so much iron and nickel that even the outer planets grew dense metallic cores. The variety doesn't stop there. Some exoplanets orbiting pulsars, the ultra-dense remnants of supernova, show compositions that defy Earth-based expectations. PSRB 1257 plus 12b, a planet smaller than Mercury, somehow survived the violent death of its host star and now orbits the stellar corpse in a system laced with heavy metals. Spectroscopic analysis suggests its surface might be studded with metallic crystals forged in the supernova's fury, making it less a traditional planet and more a cosmic scrap heap of stellar debris. Meanwhile, in the HD 219134 system, researchers found a super-Mercury with an unusually large iron core, likely the result of its formation in a metal-rich stellar neighborhood where supernova dumped extra heavy elements into the planetary mix. These discoveries are rewriting our understanding of planetary diversity. While Earth's core formed from a relatively balanced cocktail of supernova remnants, other worlds weren't so lucky, or perhaps they hit the cosmic jackpot. Systems like TRAPPIST-1, with its 7 Earth-sized planets, show wildly varying densities despite orbiting the same star. Some planets are likely rich in light elements, while others may harbor massive metallic cores, suggesting the protoplanetary disk was unevenly seasoned by supernova debris. Imagine a cosmic buffet where some planets piled their plates high with iron while others filled up on silicates. The result is a menagerie of worlds with radically different internal structures. The most extreme examples come from white dwarf systems. These dead stars often show atmospheres polluted by heavy elements, the crushed remains of planets that spiraled too close. By analyzing these stellar graveyards, astronomers have detected traces of vaporized cores containing elements like platinum and uranium in ratios that only occur in the aftermath of supernova. One white dwarf, SDSS-J0845 plus 2257, even revealed evidence of a shattered planet with a core so iron-rich it may have been the remnant of a collision between two protoplanets born in a supernova-enriched nebula. What's emerging is a galactic tapestry of planetary cores, each woven from threads of stellar explosions unique to their corner of the cosmos. Systems born near active star-forming regions might inherit cores packed with rare earth metals, while those forming in quieter suburbs could end up with smaller, less dense interiors. The next generation of telescopes, like the extremely large telescope under construction in Chile, will peer deeper into these alien planetary systems, measuring their compositions in unprecedented detail. Every strange new world adds another piece to the puzzle, helping us understand whether Earth's balanced core is the exception, or just one variation in a universe of endless possibilities. This cosmic perspective changes how we search for habitable worlds. A planet's surface conditions depend heavily on its core composition. Too much radioactive supernova material could lead to excessive volcanism, while too little might prevent the magnetic field needed to shield life. The interplay between stellar chemistry and planetary destiny is more intricate than we ever imagined, proving that to understand any world, we must first listen to the echoes of the supernova that shaped it. For all we've uncovered about Earth's cosmic ancestry, the full story remains tantalizingly incomplete. Scientists still grapple with fundamental questions like how many stellar explosions actually contributed to our planet's metallic heart. Current estimates suggest at least 2 or 3 nearby supernova enriched the solar nebula based on iron-60 and aluminum-26 ratios, but some models propose upwards of 15 distinct stellar events over hundreds of millions of years. The challenge lies in distinguishing between contributions, like trying to separate individual ingredients in a cake that's been baked for billions of years. Complicating matters are the other cosmic delivery services that may have brought heavy elements to Earth's construction site. Neutron star mergers certainly contributed gold and platinum, but what about rarer elements like thorium and uranium? Some researchers argue these could originate from even more exotic sources: collapsed stars that became magnetars, or perhaps hypernova, the ultra-powerful explosions of rapidly spinning massive stars. The recent detection of a kilonova, a neutron star collision spewing strontium into space, proves the universe has multiple ways to forge and distribute heavy metals. Then there's the puzzle of timing. Geological evidence shows Earth continued receiving fresh batches of stardust long after its formation, like iron-60, deposits from a supernova only 2.5 million years ago. This forces us to reconsider how planetary cores evolve. Rather than being static metal vaults, they might accumulate new material over eons, with each stellar explosion leaving subtle chemical traces. Advanced neutrino detectors now under development could someday track these ongoing deliveries by spotting the ghostly particles emitted when radioactive supernova products decay deep underground. The biggest unknown, whether our solar system's composition is typical or a cosmic oddity. New telescopes like the Vera Rubin Observatory are cataloging chemical abundances in thousands of nearby star systems, revealing staggering diversity. Some young stars show 10 times more europium, a classic supernova signature, than our Sun, while others are missing key elements entirely. This variation suggests planetary cores across the galaxy could range from iron-poor to metal-saturated, with profound consequences for their geology and potential to support life. What keeps scientists up at night are the gaps in our detection methods. We've identified about 20 radioactive isotopes that serve as supernova markers, but theoretical models predict hundreds more short-lived isotopes should have been present in the early solar system. Finding traces of these could reveal entirely new classes of stellar explosions that contributed to Earth's makeup. Future asteroid sample return missions might hold the key, hunting for these vanished isotopes in pristine space rocks that avoided Earth's geological recycling. The most humbling realization is how much we're still learning about our own planet. Deep mantle plumes discovered through seismic imaging might contain reservoirs of supernova material that never fully mixed into the core. Strange density variations at the core mantle boundary could represent sunken continents of metallic stardust. Every new discovery adds complexity to what we thought was a settled story, proving that Earth's relationship with the stars is far more dynamic than we ever imagined. This isn't just academic curiosity, it's a detective story where the clues rewrite themselves with each breakthrough. The same uncertainties that frustrate researchers also drive them forward. Knowing every answered question reveals new mysteries waiting in Earth's depths and the stars beyond. Many people picture supernova as nothing more than cosmic wrecking balls, violent explosions that obliterate everything in their path. While it's true these stellar detonations unleash unimaginable destructive force, that's only half the story. What often gets overlooked is their role as the universe's ultimate recyclers, tearing down old stars to build something new. Without these cataclysmic events, the building blocks of planets and life itself would never exist. Take something as ordinary as the ground beneath your feet. The iron in Earth's core, the silicon in its rocks, even the oxygen you breathe, all were forged in the hearts of massive stars and scattered across space by supernova. These explosions don't just obliterate, they transform, turning simple elements like hydrogen and helium into the complex chemistry needed for rocky worlds. It's a common misconception that supernova only bring chaos. In reality, they're the architects of structure, seeding galaxies with the raw materials for new solar systems. Another widespread myth is that supernova are rare, distant events with little connection to Earth. The truth is far more intimate. Radioactive isotopes like iron-60 found in ocean crusts and moon rocks prove our planet has been dusted with supernova debris multiple times throughout its history, some as recently as a few million years ago. These aren't abstract astronomical phenomena, they're direct contributors to Earth's composition. Even now, particles from ancient stellar explosions drift through the solar system, mixing with the solar wind and settling onto the planet's surface. Perhaps the most persistent misunderstanding is that supernova only influenced Earth's distant past. In reality, their legacy is still unfolding. The same heavy elements they created continue shaping our world today, powering geothermal activity through radioactive decay, generating Earth's magnetic field, and even influencing climate patterns over geological timescales. When a supernova's shockwave triggered the collapse of the solar nebula billions of years ago, it didn't just set the stage for Earth's formation, it became an ongoing participant in the planet's evolution. This shift in perspective changes how we view our place in the cosmos. Supernova aren't just destructive ends, they're creative beginnings. Every mountain range, every ocean, even the device you're using to watch this video contains atoms born in stellar explosions. The universe doesn't operate on a simple cycle of life and death. It thrives on transformation, where every ending plants the seeds for something new. The next time you look up at the night sky, remember those distant stars aren't just points of light. They're future supernova waiting to continue the cycle that made our existence possible. Classrooms are transforming into cosmic laboratories where students don't just learn about supernova, they experience them. Imagine a high school physics lab where instead of textbook diagrams, teenagers manipulate 3D simulations of collapsing stars, watching in real time as shockwaves compress virtual gas clouds into planets. These interactive tools bridge abstract concepts to tangible understanding, letting learners adjust variables like stellar mass or explosion energy to see how each change alters the resulting elemental cocktail. One particularly powerful simulation developed by NASA, a Universe of Learning initiative, allows students to inject different supernova remnants into a protoplanetary disk, then track how those metals distribute across forming worlds, revealing why Earth's core ended up with its unique composition while Mars developed differently. Hands-on activities take this further with tactile models that make stellar physics accessible. Some classrooms use layered acrylic spheres filled with colored beads representing various elements, squeeze the model just right, and it explodes, scattering beads across a map of the solar system to show where iron, gold, and uranium would accumulate. Others employ augmented reality apps where pointing a tablet at a poster of the periodic table overlays which elements came from which types of stellar deaths. The most innovative programs even partner with university labs, giving students access to real meteorite samples under microscopes, searching for those telltale iron-60 inclusions that prove Stardust's journey from supernova to classroom. The impact goes beyond memorizing facts. When middle schoolers in Colorado used seismic data from the Deep Earth Carbon Observatory to model how radioactive supernova elements still heat Earth's core, they discovered firsthand how astronomy connects to geology and why volcanoes erupt. In Australia, a high school team analyzing lunar soil data identified an iron-60 spike matching a known supernova event, publishing their findings in a peer-reviewed journal. These experiences transform supernova from distant fireworks to personal history, helping students grasp that the calcium in their bones and the iron in their blood were literally forged in stellar explosions. Educators are finding creative ways to scale these tools globally. Virtual reality field trips now let students worldwide don headsets to stand on the surface of a neutron star or witness a supernova shockwave compress a gas cloud into planets. Open-source platforms like the Sloan Digital Sky Survey's SkyServer put real telescope data at kids' fingertips, allowing them to hunt for supernova remnants in other galaxies while learning the same analysis techniques professionals use. Even board games have entered the mix. One popular title, Stellar Forge, has players compete to build the most chemically diverse planetary system by strategically collecting supernova-produced elements. The ripple effects are profound. After Texas schools introduced a curriculum tracing smartphone components back to their stellar origins, gold from neutron star collisions, rare earth metals from supernova, participation in astrophysics electives tripled. Similar programs in Norway now train teachers to use supernova chemistry as a gateway to discussing everything from nuclear physics to environmental science, proving how cosmic events can unify disparate STEM fields. What begins with a classroom simulation of a dying star often blossoms into lifelong curiosity, with former students crediting these immersive experiences for their careers in volcanology, materials science, and even medical research tracing supernova-produced isotopes in cancer treatments. This educational revolution reaches beyond traditional schools. Science museums from Tokyo to Chicago now feature walk-through models of supernova debris fields, where visitors physically move through suspended particles that sort into planetary cores based on density. Public libraries loan out cosmic chemistry kits with spectroscopes to analyze simulated stardust, while planetariums debut shows projecting real-time supernova detections from neutrino observatories onto their domes. The message is clear: understanding Earth's core isn't just for geologists, it's a multidisciplinary adventure spanning physics, chemistry, and astronomy, accessible to anyone curious enough to explore. At its heart, these tools do more than teach science, they foster cosmic perspective. When a seventh grader manipulates a simulation to see how their hometown's bedrock contains atoms from a star that died billions of years ago, abstract concepts become visceral truths. That moment of connection where the unimaginable scale of space and time collapses into personal relevance is where future scientists are born. And in classrooms across the world, that spark ignites daily, proof that while supernova may have shaped Earth's past, their educational legacy is shaping tomorrow's discoverers. The rush to mine asteroids for precious metals isn't just a gold rush. It's a race against time to preserve the universe's oldest history books. These floating space rocks contain untouched records of supernova explosions and planetary birth, with some meteorite grains predating our solar system itself. Imagine cracking open an asteroid only to discover layers of stardust that reveal which stars contributed to Earth's core, only to have those clues vaporized in an industrial refinery before scientists can study them. That's the ethical dilemma facing space mining today: how to extract resources without erasing the cosmic fingerprints that tell us where we came from. Consider the asteroid Psyche, a metallic world believed to be the exposed core of a failed planet. Mining companies eye its trillions of dollars worth of iron and nickel, but planetary scientists see something irreplaceable, a pristine example of how heavy elements from supernova clumped together during solar system formation. Drilling into Psyche could answer why Earth's core has the exact mix of metals it does, or reveal whether our planet's magnetic field is a cosmic fluke. Yet under current space law, whoever reaches Psyche first could legally strip mine it without preserving a single sample for research, potentially obliterating clues about stellar explosions that happened billions of years before humans existed. The problem isn't just about preserving individual asteroids, it's about protecting the context of the solar system's chemical evolution. Certain rare isotopes only form in specific types of supernova, and their distribution across different asteroid families acts like a treasure map showing where and when stellar debris enriched our cosmic neighborhood. Mass mining could scramble this evidence forever, like bulldozing an archaeological dig before cataloging the artifacts. Even seemingly barren asteroids hold microscopic diamonds with trapped noble gases, time capsules from stars that died before our sun ignited. One commercial mining operation using indiscriminate extraction methods could accidentally destroy more stellar archaeology than all meteorite collections on Earth combined. Solutions exist if we act now. Proposed ethical frameworks suggest designating certain asteroid classes as scientific preserves, off limits to mining until thoroughly studied. Others advocate for mandatory sample return protocols, where mining ventures would be required to set aside portions of material for research, similar to how terrestrial mining companies sometimes fund archaeological surveys before digging. The most promising ideas involve collaboration between corporations and scientists, like NASA, partnerships with private lunar landers that prioritize data collection alongside commercial activities. Imagine mining robots equipped with spectrometers, scanning each asteroid layer before extraction, and building 3D compositional maps that outlive the mines themselves. What's at stake goes beyond pure science. These asteroids don't just contain metals, they hold the answer to whether Earth's perfect balance of supernova ingredients was luck or inevitability. Understanding that could determine which star systems we target for future exploration, or even how we search for life elsewhere in the galaxy. The decisions we make in the next decade about space mining ethics will echo for centuries, determining whether we become careful cosmic archivists or reckless bulldozers of the universe's memory. The iron in these asteroids waited 4.5 billion years to tell its story. It's our responsibility to ensure it gets heard. Solving the riddle of Earth's core composition isn't a job for any single scientist. It takes a cosmic detective squad with specialties spanning the universe. Astronomers track dying stars, geologists decode ancient rocks, and particle physicists recreate stellar explosions in labs no bigger than your living room. This interdisciplinary tango is revealing connections no single field could uncover alone. Picture an astronomer analyzing light from a distant supernova remnant while, at the same moment, a geologist chips a meteorite sample in Antarctica, and halfway across the world, a physicist bombards atoms in an underground accelerator. Though separated by continents and specialties, they are all piecing together the same grand story written in atomic ink. The breakthroughs happen at these intersections. Take the case of iron-60 isotopes found in deep-sea crusts. Geochemists initially mistook them for contamination until nuclear physicists confirmed their extraterrestrial origin by matching decay patterns to supernova models. Meanwhile, astronomers pinpointed likely culprit stars by cross-referencing the isotope's age with stellar motion maps from the Gaia Space Telescope. This three-way collaboration turned what could have been an odd geological anomaly into proof that Earth was dusted by stellar debris just 2 million years ago. Laboratories have become melting pots for these disciplines. At facilities like CERN, geologists work alongside particle physicists to simulate how iron behaves under core pressures by smashing ions together at near light speeds. Their findings feed directly into astrophysicists' supernova models, which in turn help geophysicists interpret seismic waves rippling through Earth's interior. It's a continuous loop, each discovery in one field refining questions in another. When mineralogists discovered a new form of iron oxide stable at core conditions, astronomers immediately adjusted their estimates of how much oxygen supernova could have delivered to young planets. The tools bridging these fields are as innovative as the discoveries themselves. Mass spectrometers once reserved for geology now analyze stardust from NASA missions, while algorithms developed to map earthquake zones help astronomers reconstruct shockwaves from ancient supernova. Even art plays a role. Data visualization specialists transform abstract numbers into 3D models that let researchers literally walk through simulations of stellar explosions or Earth's churning core. What makes this collaboration so powerful is how it transforms limitations into strengths. A geologist might spend years extracting a single crystal from Earth's oldest rocks, while an astronomer observes phenomena light years away that they can never touch. But combine their perspectives, and suddenly the geologist's microscopic sample becomes a lens to view the cosmos, and the astronomer's distant supernova offers context for the geologist's tiny time capsule. The iron in Earth's core becomes both a geological feature and an astronomical message decoded through physics. This teamwork is rewriting textbooks daily. When neutrino detectors deep in Antarctic ice caught particles from a distant supernova, the same week a new mineral was discovered in a meteorite. The combined data revealed how shockwaves can forge crystals impossible to create on Earth. Now museums display these alien minerals beside photographs of the supernova remnants that likely birthed them, a tangible link between celestial events and terrestrial chemistry. The most exciting collaborations are yet to come. Proposed missions to drill into Earth's mantle or land on metallic asteroids would unite planetary scientists, engineers, and astronomers in ways never before attempted. As these disciplines continue merging, we're not just learning about Earth's past, we're pioneering a new model of discovery where the boundaries between stars and stones, between cosmic and terrestrial, blur into irrelevance. The universe doesn't compartmentalize its secrets, and neither do the scientists unraveling them. Every discovery about Earth's core peels back another layer of cosmic history, yet with each revelation, the universe seems to whisper even grander mysteries waiting to be solved. What if our planet's iron heart holds clues not just about past supernova, but about events we haven't even imagined? Future technologies could transform how we listen to these stellar echoes. Imagine neutrino observatories detecting the faint radioactive decay of supernova elements still pulsing in Earth's depths, or quantum gravity sensors mapping the core's composition with atomic precision. Some researchers speculate that pockets of exotic matter remnants of neutron star collisions might lurk near the core mantle boundary, their presence hinted at by anomalies in seismic wave patterns. The next frontier might lie in stellar archaeology, using AI to reconstruct the solar system's birth environment. By feeding data from meteorites, lunar samples, and deep-sea isotopes into machine learning models, scientists could simulate thousands of possible supernova combinations that match Earth's unique metal fingerprint. Already, early algorithms have suggested our solar system may have formed near a rare hypernova, a stellar explosion orders of magnitude more powerful than typical supernova, which could explain puzzling concentrations of platinum in Earth's mantle. Future upgrades to particle accelerators may even let us recreate miniature versions of these extreme cosmic events, watching in real time as they forge the same exotic isotopes now buried beneath our feet. Perhaps most tantalizing are the unanswered questions about timing. Why does Earth's core show evidence of multiple supernova enrichment events spread over hundreds of millions of years? Did our young solar system drift through successive waves of stellar debris like a ship sailing through radioactive fog? Upcoming space missions like the European Space Agency's Ariel telescope will analyze the atmospheres of distant exoplanets for similar isotopic patterns, revealing whether our planet's staggered stardust inheritance is unique or a common feature of galactic evolution. Closer to home, drills capable of reaching the Mohorovicic discontinuity, the boundary between Earth's crust and mantle, could retrieve rocks untouched by surface weathering, potentially preserving pristine supernova signatures from the planet's infancy. This isn't just about satisfying scientific curiosity, it's about rewriting humanity's origin story. If we discover that certain heavy elements in Earth's core originated from a specific type of supernova, now vanishingly rare in our galactic neighborhood, it would suggest our solar system formed during a special era of cosmic chemical abundance. Alternatively, finding unexpected isotopic ratios might hint at entirely unknown stellar processes that no longer occur in the observable universe. The answers could redefine our place in the cosmos, showing whether Earth's composition was inevitable given local stellar demographics, or the improbable result of a celestial lottery whose winning numbers we're only now learning to read. The tools to uncover these secrets are already taking shape. Deep underground in abandoned gold mines, ultrasensitive detectors await the telltale flashes of light produced when decaying supernova atoms interact with liquid argon. On the ocean floor, robotic crawlers systematically scan crust layers for iron-60 hotspots that could trace our solar system's passage through ancient supernova remnants. Even ordinary smartphones are contributing. Citizen science apps let users report meteor sightings, expanding the network of recovered space rocks that might contain stellar grains predating the Sun. What makes this quest so electrifying is its unpredictability. Like opening a time capsule buried by the universe itself, every probe into Earth's core could reveal anything from humdrum confirmation of existing theories to paradigm-shattering anomalies. Maybe we'll find evidence that a nearby supernova's gamma ray burst scorched Earth's surface just as life was beginning, or uncover metals so exotic they defy current physics. The only certainty is that the story written in our planet's depths is far stranger and more magnificent than we've dared to imagine, and the next chapter of discovery is waiting for those bold enough to keep digging. From the fiery hearts of dying stars to the molten core of our planet, we've traced a journey written in atoms, one that began with unimaginable cosmic violence and ended with the ground beneath our feet. Every earthquake that rumbles through the continents, every shimmering aurora dancing at the poles, even the magnetic field shielding life from solar storms, they all whisper the same truth: Earth is more than just a rock floating in space. It's a living archive of stellar history, a testament to the universe's endless cycle of destruction and creation. Think about the iron in your blood, the gold in your jewelry, the uranium powering nuclear reactors. None of it originated here. These elements were born in the final, cataclysmic moments of massive stars, scattered across the cosmos like seeds in a galactic wind. Over billions of years, gravity gathered those scattered atoms into planets, sculpting them with collisions and cosmic chance until one world, our world, ended up with just the right mix of metals, radioactive heat, and magnetic protection to cradle life. It's a story of precision so perfect it feels like fate, yet so fragile it could have unraveled at any moment. If that supernova had erupted a light year farther away, if the solar nebula had collapsed a million years later, if Earth's core had cooled too quickly, none of us would be here to ponder these mysteries. But the story doesn't end with Earth. The same processes that shaped our planet are unfolding right now in distant star systems. Telescopes have spotted young worlds orbiting metal-rich suns, their cores possibly forming from stardust even more exotic than our own. Some may become barren rocks, their magnetic fields too weak to hold atmospheres. Others might evolve into ocean worlds or super-Earths with cores so massive they generate magnetic shields far stronger than ours. Each is a natural experiment, testing how variations in stellar chemistry write the destinies of planets. What's humbling is realizing we're only beginning to decode this cosmic language. Every drill core pulled from the ocean floor, every meteorite cracked open in labs, every seismic wave mapped through Earth's depths, they're like sentences in a book we're still learning to read. The iron-60 isotopes in ancient crustal rocks, the tungsten anomalies in asteroid samples, the neutrino signals from decaying uranium deep underground, these aren't just data points. They're messages from the stars patiently waiting for us to piece together their meaning. So the next time you pick up a coin or feel the weight of a metal doorknob, pause for a second. That ordinary object is anything but ordinary. It's a fragment of a star's final act, a relic of an explosion so powerful it defies comprehension. The universe took something violent and destructive and turned it into the foundation of mountains, the spark of technology, even the hemoglobin carrying oxygen through your veins. That's the real magic of science, not just uncovering facts, but revealing connections that tie us to the cosmos in ways we're only starting to understand. If this journey through stardust and seismic waves has sparked your curiosity, you're already part of the story. Every question asked, every comment shared, every subscription that helps this channel grow, it's all part of humanity's collective effort to read the universe's grand narrative. So let's keep exploring together. Hit that like button if you enjoyed the ride, subscribe to dive deeper into the mysteries of space and time, and drop your thoughts below. What cosmic clue fascinates you the most? Until next time, keep looking up and down because the ground beneath you holds just as many wonders as the stars above.